All right, 10.3, we are using chords, not chords, chords. Chords, like an extension chord. Remember what a chord is. Here's a circle. A chord is a segment through the circle, but it has two endpoints on the circle, right? This is a chord. Another example would be this. This is also a chord. As long as both endpoints are on the circle, it's a chord. I'm going to be learning about that today. We're going to skip the majority of the first part here, and we're going to get down into definitions. We know chord, arc, and diameter from the last two lessons, so we should know those. Let's get into these theorems here. The congruent corresponding chords theorem. In the same circle or congruent circles, okay, depending on what we are given here, two minor arcs are congruent if and only if their corresponding chords are congruent. So down here, we look at the statement. Arc AB is right here, is congruent to arc CD on one condition. AB, okay, this chord here has to be congruent to chord CD. Okay, or DC, it doesn't matter. Okay, but those two chords have to be congruent. If the chords are congruent, then their arcs are congruent. The next one, okay, important one for today. The perpendicular chord bisector theorem. If a diameter, remember diameter, that is a chord through the center of my circle. It splits my circle in half. If a diameter of a circle is perpendicular to a chord, okay, remember perpendicular makes a 90-degree angle, then the diameter bisects the chord and its arc. So look in here again. If EG is here, okay, that's our diameter. If it is a diameter, which it is, it's a chord through the center. And EG is perpendicular to DF, which it is, right? It is, because we have a 90-degree angle here, so it is perpendicular. Then HD is congruent to HF. HD is congruent to HF. It splits it in half. Okay, so if it's a perpendicular to the diameter, then the chord is split into two halves. Okay, that also says something about our arcs. It says that GD will then be congruent to GF. Okay, it bisects, it cuts it in half. Everything, our chord and our arcs. Okay, but it has to be a diameter. It can't just be any other chord. The perpendicular chord bisector converse is just saying that kind of in reverse. If QS is a perpendicular bisector, QS is right here. If it's a perpendicular bisector of TR, then QS, right? So if these two things are congruent, then we know QS is the diameter. Okay. All right. And the last one here. Equidistant chords theorem. In the same circle or congruent circles, again, based on our drawing or what we're given, two chords are congruent if and only if they're equidistant from the center. So AB is right here. That's congruent to CD if and only if they are the same distance, meaning EF has to be the same distance as EG. Okay. Then they would be congruent. Let's try some extra practice, because again, these theorems make more sense the more practice we go through. In 1 through 4, find the measure of the arc or chord in circle Q. Number one, find the measure of WX, arc WX. That's this arc here. Find this measure. Remember, arcs are measured off of the central angle, okay? And we know that this angle is 42. We have vertical angles here. This is also 42. All right, next one is YZ, just the length from Y to Z. Based on our information, we know that this was congruent to this. We should know that 3.6 is equal to YZ. WZ. WZ, these are two chords. I wish they would be a little more specific in our drawing and tell us that they're the same distance to the center. These two chords are the same distance to the center. So they are congruent chords. It's 9.2. Yeah, same as this one, 9.2. And number 4, the measure of arc XY, from X to Y. So we have to do a little bit more math here. We know that this is 42 degrees here. We know that this is 42 degrees here. This arc has to be congruent to this arc. Okay, because we have congruent chords there. So what we have to do is we have to take 360 and subtract from what we have already. So that's 360 minus 84, which if you did the math, it'd be 376. We're actually going to divide it by what we have left. We need to divide that by 2 equal parts because XY and WZ are the exact same. 376 divided by 2 is, let's see here, 188, I believe. 188. I need to grab a calculator just to make sure. Oh, I messed up. Sorry, I am an idiot. 360 minus 84 is 276. Ah, I knew that did not seem right. That's why I had to double check. We're going to divide that by 2. Whew. Divide that by 2, and it is 138. Okay, that makes more sense. So the arc of both of these is 138 degrees. So arc of XY is 138. Okay. In 5 and 6, it says find the value of X. So we have a diameter here because this is a chord that goes through the center of our circle. This 90-degree angle is very useful. This tells us that the two parts, PT and RT, have to be congruent because it bisects. All right, it's a 90-degree angle. It tells us it's a bisector. So we can set up the equation 2x minus 4.1 is equal to x minus 0.5. This is where we just have to solve algebraically. Let's subtract x from both sides. To get x minus 4.1 is equal to negative 0.5. And we're going to add 4.1 to both sides. Just get us x by itself, which is what we want, and x is equal to 3.6. That's for number 5. It's going to be the same process for number 6. Okay, we have a diameter. We have a 90-degree angle. So that tells me that these two are congruent. Set it up as an equation. 3x minus 5 is equal to 2x plus 1. I'm going to subtract 2x from both sides. I'm going to add 5 to both sides. Okay, so my final answer, I get x is equal to 6. Next part. It says find the radius of the circle. So this is a little more challenging. Remember, the radius goes from the center of our circle to the edge of our circle. It's good to know that we have a right angle here, because that tells us that this is a bisector, these two sides. Okay. And since we have 3 and 3, we know that 3x plus 2 is equal to 5x minus 2. So we have to solve for x first. When you set them equal to each other, solve for x. So I'm going to subtract 3x from both sides. I'm going to get 2x. I'm actually going to add 2 to both sides. Sorry, I kind of missed that stuff. So we're going to add 2 to both sides. We'll subtract 3x, so add 2 here. Okay, kind of doing 2 steps in one, which is fine. You can do that algebraically. 2 plus 2 is 4. So we get 2x is equal to 4. To solve for x, we're just going to divide by 2. So x is equal to 2. Okay, that's a good thing. That's a good thing to know. If we plug x in to our equation here, we'll find, what is that, FD? We'll find this length. Okay, so 3 times 2 plus 2, which is 6 plus 2, which is 8. Okay, so we know that FD is 8. Now I'm going to erase this and kind of make some room here for another drawing. If we know this is 8, FD is 8, okay, and PE is a bisector, we know that this half is 4, and this half is 4. Okay, now we're going to get to this part of the question, finding the radius. What we can do is draw a segment from our center to one part of our chord, okay, where it connects. That's our radius. And we can say that is going to be R. Now you could have done this for any part, right? Because you know that this is 8 as well. You know that this is 4 and this is 4. You could have done the same exact thing right here, which is R. Okay. Either way, what you create or what you have is a right triangle with 2 sides already given, or 2 sides that we have, 4 and 3. We need to find the hypotenuse. And how do we do that? Using Pythagorean theorem. R squared is equal to 4 squared plus 3 squared. Okay, find that length. Find R. R squared is equal to 16 plus 9, which is 25, is equal to R squared. You got to take the square root. So R is equal to 5. And that is our final answer for number 7. So kind of a lengthy process, right? But we can do it. We can solve. If I go to number 8, okay, again, we have 2 chords here that are the exact same length. They give us the length. It's 20. So if they're equal, then they're both the same distance from the middle. So we know that 4x minus 5 is equal to x plus 4. We can solve for x by setting these equal to each other. And we're going to subtract x for both sides. Gets rid of it here. We're going to add 5 to both sides. So we get 3x is equal to 9. Another step, just divide by 3. So we get x is equal to 3. So we want to learn, or we want to know what this length is or this length. We'll just plug x in. So 3 plus 4 is 7. Which means this is 7. Now, our radius goes from the center to one of our edges of our chord. Okay, that's R. We know this leg, it's 7. Do we know this part? Yes, we do. Okay, it's 20 divided by 2 because we have a bisector with that right angle, so this is 10. And solve it the exact same way we did the last problem, where we have R squared is equal to 7 squared plus 10 squared. R squared is equal to 49 plus 100, which is 149. And the square root of 149 is 12 point, take out a calculator, you got to think about this one. Square root of 149 is 12.2. So those last couple problems are probably the toughest of this lesson. But it's just breaking it down and solving for the radius. Okay, if you have questions on any of this, please send me an email or talk to me at school.